Assalamualaikum and greetings everyone. Welcome back. We are still on sketching graph of vector function. In the previous video, I've shown you item 1 where our vector function is a curve on the xy plane. Apart from the method that I've shown you in the previous video where we form a table and then get a few values of t, get the endpoints of our position vector and then plot the position vectors and connect all the endpoints of the position vectors. We can also plot our vector function item 1 using a set of parametric equations. Okay, so for example 1, the set of parametric equation for our vector function is x is equal to t, so that is the x component, and y is equal to t squared, which is the y component. So now by eliminating parameter t, we can write down y as x squared since t is equal to x, and you can see that this is an equation of a parabola. Okay, so for a curve on the xy plane, you can represent your curve using vector valued function as such, or using set of parametric equation as such, or as a function y in terms of x, or x as a function of y, or an equation fxy equals a constant. So there are more than one way to represent a curve on the xy plane. Alright, but for a curve on the in the xyz space, you have no choice. You have to use a vector valued function or set of parametric equation. Okay, now let's proceed to example 2. Okay, in example 2, we have a vector function 3 sine ti minus 3 cos tj plus 2k. Alright, I need more room. Okay, before we fill in this table with t's, x, and also the position vectors, let's get the parametric equation for our vector function r here. Using looking at the vector function r, we can see that the parametric equation for x is equal to 3 cos t, while the parametric equation for y is going to be the y component of our vector function r, so that is equal to negative 3 sine t, and the parametric equation for z is 2. Okay, so from the set of parametric equation of our vector valued function r, we can see that z doesn't change. Z is always 2, but x and y varies. Okay, which means that for our points x, y, z, remember we have points x, y, z for different values of t. The z coordinate is always 2, only x and y varies. So I'm going to use the same technique that I've shown you for example 1, item 1, where we eliminate parameter t to get an equation y in terms of x. Okay, we're going to do the same thing for example 2. Okay, so now we know that our curve is going to be on z equals 2 plane because z is always 2. Okay, so our curve is going to be on z equals 2 plane. Okay, now what we're going to do is we're going to eliminate parameter t just like in example 1. So from here, from the parametric equation for x, we can see that cos t is equal to x over 3, while sine t is equal to negative y over 3. And then we're going to use the trigonometric identity where cos squared t plus sine squared t is equal to 1. So this is from the trigonometric identity. So from here, cos t is x over 3, so cos squared t will be x squared over 9, and since sine t is equal to negative y over 3, so sine squared t will be equal to y squared over 9, and this should be equal to 1. So rearrange the equation, we can see that we end up with x squared plus y squared equals 9, which is an equation of a circle. Okay, so now we know that our curve, our vector valued function RT, is going to be a curve. So our vector function RT will be a curve, a circle, because we know now our curve is going to be a circle of radius 3 on the z equals 2 plane. Okay, so our curve for the vector valued function r is going to be a circle of radius 3 on z equals 2 plane, because the z component is always 2, meaning that z doesn't change. So our curve is going to be on z equal 2 plane, and it's going to be a circle. So let's say we're going to plot this circle of radius 3 centering at x0, y0, z equals 2. Okay, so let's say 1, 2, 3, 4. Okay, let's say that's a 2. Okay, so what we're going to do is we're going to sketch a circle of radius 3 on z equals 2 plane. Okay, so this is 1, 2, so we have 1, 2, 3, so it will go through this point. So this is 3, and here we have 1, 2, 3, so that is -3. So it will go through this point, that point. This is a 2, and let's say that's a 1, 2, 3. So this is 3, and here we have 1, 2, 3. So this is equal to -3, right? And then we're going to sketch a circle. I'm going to use blue. Okay, so we have a circle of radius 3. Not quite there. Okay, hang on. Let's see here. Still, I guess. Okay. How about now? Not quite. Hang on. Also no. Okay, I think I better use my freehand. Okay, not very pretty then. Okay, let's see. I should connect this point. Okay, so we have a circle of radius 3 centering at x0, y0, z2. Okay, now what we want to sketch is a vector valued function. So when a vector, we have a direction. So now we don't know whether our circle here is in an anti-clockwise direction or clockwise direction. So for that, we need to get a few position vectors, because the direction of your vector valued function depends, it will be the same as how t increases. Okay, it's in the same direction as t increases. So we need a few position vectors. Okay, so going back to our table here, since our t involves, our parameter t is really an angle, so I'm going to use pi. So we need negative pi over 2, so we take a few negative and positive. Okay, alright, now when t is negative pi, we know that cos negative pi is -1, so x is going to be -3. Sine pi is 0, so y is going to be 0. Z here is always 2, so we have 1 point. So this is a point, which is the point at the end of the position vectors. So we have one position vector when t is -pi. So here I'm going to use this pointy bracket to represent a vector. So we have -3i plus 0j plus 2k. Now when t is -pi, we know that negative pi over 2. Cos negative pi over 2 is 0, so x is going to be 0 now. Negative pi over 2, sine negative pi over 2 is negative 1, so y is 3, and z is always 2. So now we have the endpoint of our position vector. So this is the endpoint, and this is our position vector, which is at 0i plus 3j plus 2k. Okay, note here that I'm using the pointy bracket instead of using I, j, and k. The reason is I want to save some space. Alright, now when t is 0, cos 0 is 1, so x is now going to be 3. Sine 0 is 0, and z is always 2, so we have another point, 3, 0, 2. And another position vector, which is at 3i, 0j, 2k. And when t is pi, cos pi is 1. So now we have, cos pi is negative 1. So that will be negative 3. And sine pi is 0. Z is always 2. So we have negative 3, 0, 2, and now we have another point, another position vector, sorry, negative 3i plus 0j plus 2k, and the last is, oh, hang on, I should be pi over 2, sorry, I'm going to erase this. That one is for pi. Okay, I'm missing pi over 2, sorry about that. Now when t is pi over 2, cos pi over 2 is 0, so now x is 0 and y is negative 3 and z is 2, so we have another point, 0, negative 3, 2, and we have another position vector which is equal to 0i minus 3j plus 2k, and the last t is pi. Cos pi is negative 1, so we have negative 3. And sine pi is 0, and z is always 2, so we have another point, negative 3, 0, 2, and we have another position vector which is negative 3i plus 0j plus 2k. Alright, now I'm gonna sketch our position vector. So remember, position vectors starts at the origin. Okay, from the origin, it starts from the origin. Okay, so let's see. When t is negative pi, so we're going to sketch this vector valued function, position vector. So we start from the origin. Okay, we start from the origin, and then we have negative 3i. So we move 3 units backwards up to here. And then 0j, meaning that we don't move to the left or right. And then we have plus 2k, so start there. So we have one position vector. That is for r equals t equals negative pi. Let me write that. This is r negative pi. So that is one position vector. Okay, now we need another position vector when t is negative pi over 2. So we're going to sketch this position vector. So we have 0i, so we don't start from the origin, we don't move backward or forward because the x component is 0, and then we have 3j excuse me, so we move 3 units to the right, and then plus 2k, so we stop here. So we have one position vector, another position vector. So this position vector is when excuse me, t is negative pi over 2. So this is negative pi over 2. And when t is 0, we get this position vector, 3i. So we move from the origin 3 units forward, and then we don't move to the left or right because j, the y component is 0, and then we move 2 units up. So we have this position vector. Okay, so I only plot position vectors. From there we can guess the direction of our vector function r. So this is when t is 0. Okay, so now we have 3 position vectors. So remember, the direction of our vector is the same direction when t increases. Okay, so here we have this is a point on the curve when t is negative pi over 2. This is a point on the curve. This is a point on the curve here when t is negative pi over 2. And this is where we are on the curve when t is negative pi over 2. And this is where we are on the curve when t is 0. So from there you can see that the direction of t would be clockwise direction. Okay, so the direction of our vector valued function would be clockwise direction, like so. Okay, so the blue curve is our vector function r. The green vector is the position vector. Okay, so that is our should be the other way around. Yeah. Okay, position vector. Hang on. Position vector r at t naught. Position vector r at t, different values of t. I'm gonna erase that. Okay, so here I'm only sketching 1, 2, 3 position vectors. But of course, if you sketch another 2 here for pi over 2 and for t equals pi, you get another 2 position vectors. Okay, so that's how you plot or sketch a graph for a vector valued function. Here I'm since one of the components is a constant, so we can figure out the curve where our vector value function curve is, and then to get the curve using x and y, what we do is we eliminate parameter t and we end up with this equation. So from this equation we know that our curve is going to be a circle on the z equals 2 plane, since the z component is always 2, it's a constant. Okay, so that is another example of sketching a vector valued function. Thank you.